Okay. Connect this. All right, so here we are. Last time we were doing notes, what we were talking about was we were talking about how when you have these curved lines here with the acceleration and deceleration, or accelerating and decelerating, that what you're having there is a change in velocity. All right. Now, this change in velocity we say it's a vector quantity, which means that it has magnitude and direction. So the magnitude is the speed, and the direction. So in order to have a change in velocity, yes? Yeah. In order to have a change in velocity, you need to have a change in either the speed or the direction. It can be both. But if one of those two changes, then you will have an acceleration. Now, so for instance, if an object is moving at the exact same speed, and then all of a sudden changes direction, that was an acceleration. Okay. Now, so basically, if you think of going in the circle going in a circle is a constant acceleration. Because you're constantly changing directions if you go in a circle. Okay. Now, what I want you to understand about that acceleration, though, is that what it represents is the application of a force. In order to have an acceleration, you have to apply a force to the situation. And in fact, it is like a barometer of the force. The stronger the force, the greater the acceleration. Now, how do we know when acceleration occurs? As well, and this is kind of a subjective way of doing it, but it actually works really well. And the truth is that we do not feel speed, right? We don't feel really when something is going fast. What we feel is acceleration. Right? For instance, if you are going on a ride, let's say you're going a couple states away and you're driving, and you're in the car and you put cruise control on and cruise, 60, 70, whatever miles an hour. Once you get, yes. Oh, yeah, content library under acceleration. Once you get up to that speed, then you can kind of just relax, right? Some people can just sort of read, maybe sleep, whatever. But you don't really feel that you're going that fast because you get to that speed and you get to the fancy science word for that is stasis, meaning that everything stays the same, like where we get the word static. In our brain, yes.
Why can we feel it like when we're speeding up?
Well, I'm going to get to that in a second. Yeah. Our brain does that because there are times where, like if we were in this like constant alert state, we would wear ourselves out, right? So, and cats are experts at this, right? You have a cat and the cat just kind of lays down and they can take what they call little cat naps. So they just chill, right? And then they get right back up and be super alert in the next second. But what they're doing is they're conserving energy. Their brain is conserving energy. And that's what you're doing when you get that speed and you're not really recognizing that you're going that fast. You can look out the window and see things flying by, but you don't physically feel that you're going that fast, right? You're in this nice protected environment. You don't have the wind hitting you, all those things. Maybe you're on a motorcycle, it's a little bit of a different feel. But if you're in that car, you're in a van, SUV, whatever, you're going at 70 miles an hour and somebody cuts your mom off as you're driving. And she has to brake, she has to swerve. You feel that, right?
Yeah.
If you're sleeping, you're awake right away. Right? Again, that's survival. Because your brain is saying, okay, something's different. And I need to pay attention to this. And if you think back to our like way ancient forebears, that was, if something like that changed, right? They were like falling out of something. Something you needed to pay attention to it, or you would die. Right? Yes.
Isn't that why you like when you read a book and it's like a living card, you get like corset?
Some people do because they can still feel that, like if you're really sensitive to those vibrations, usually like if your ears, what it is you don't have great equilibrium in your ears, so you're still feeling the vibrations a little bit more than the average person. And then you're trying to stare at a single thing, your brain doesn't know what to do with that. And it gets confused, and that's when motion sickness comes along, right? And it's a lot worse if you go, if you're on a boat, trust me. It's a lot worse on a boat than it is in a car. So, because there you got real differences, and your equilibrium is way off, right? But yeah, but that's what it's all, and then there's some people who have pretty good equilibrium, like I've never had a problem reading the card. My wife can't at all, but it's never bothered me. You know, people are different, and the way people's heads are put together are different. So, but anyway, so we feel acceleration, right? Whether something is speeding up or slowing down, right? Like if you're driving and all of a sudden somebody has to slam on the brakes, you know it. Because and that's like when, as you guys are learning how to drive, you probably hear that a lot, that you have to learn how to like subtly brake. Because it's not very comfortable for your passengers to be jumping around, and as well for the other drivers. Okay. So, but roller coaster makers really take advantage of this, and that's what they try to really put into the rides, is acceleration. Right? That's why they have steep hills and big hills that have these big drops, right? In fact, there are rides where that's all it is, it's just the one drop. Right? They'll throw you up in the air and then you fall down, because then you're accelerating one way and you're changing it. It wouldn't be a very fun roller coaster if you didn't have those accelerations, because then you just like keep going one speed, and that's like the train ride when you're looking at animals and stuff. It's fine, you know, you like to look at the animals, but if you're getting on a roller coaster, that's not why you're getting on a roller coaster. You want to have that kind of stimulatory experience where you have the big changes going on. The big changes in your environment. So really, what you want is fear. You want to feel like you're going to die and then live at the end of the ride. That's really what roller coasters are about. Right? That's like the unconscious, the motivation behind it is to kind of conquer that death fear.
Feel like you're gonna die.
Well, I mean, basically, if you weren't in a safe car, if you went down that fast, you would die.
Yeah.
Right? So, but your unconscious brain, that's what it's experiencing.
Gotcha.
Right? Because you have this brain that is like your animal brain. Like if you had your cat or something, and you took them on the roller coaster, you know, you would be scratched pieces by that cat. Because that cat's not going to think that that's amusing. Because the cat doesn't have that logical, okay, I know that this is safe, but I still have this feeling back here that this is safe, so it's all good, right? There's some people where they have that feeling back there, and that's way too powerful, and they hate roller coasters. They don't want to get on it, right? Because that fear overcomes it. Yes.
Is that why it's like houses so much?
What?
Is that why it houses so much? Because it's like being scared.
Exactly. Yep. Same thing. It's all of our challenge to conquer death, right? But we can logically overcome the fear. Some people have that fear too much, and they can't really overcome, or they don't really want to. Right? And those are the ones that don't, maybe, or they'll get on a ride and then they won't do it again. Or if you watch on YouTube the people that get on the shops where there's like slingshot rides, and they're screaming or they pass out because they have such that response, that physiological response, that their body doesn't know what else to do. Right? But that's what we want to do. Where people jump out of airplanes or jump off like this, hang glide and stuff. Same idea, right? But anyway, going back to this, it's all related, I'm sure. But it's okay. I'm not above digression. Anyways, so when we have this, Beck always has these nice, neat math things. I would feel bad erasing them, so I'll just try to write it up here as best I can. So if we have our acceleration, then we need to look at this in terms of the units. This is going to be our equation right here, right? Where the VF is the final velocity. And what that means is, what is the velocity at the end of the whatever time interval you're looking at, right? And it'll tell you that in the problem, from the start to the end of the problem, where the velocity ends up is the final velocity, V sub F. Write that better. The V sub I is what we call the initial velocity. Right? And then T is time. The time required. So if we look at this, acceleration then can be changed by increasing the amount of the difference in the velocity, right? If we increase the difference in the velocity, then we will increase the acceleration. Or what can we do with time? What would increase the acceleration? More time or less time? Less time, right? And if you think about braking, you could brake for a stoplight, and you get right up to the stoplight and then jam your brake down and stop. That would be a big deceleration, a big negative acceleration, right? Or you can do it like you're supposed to and start way back where and see the light turn red and you start slowing down and slowing down and slowing down. Because that's a nice, easy acceleration.
It's a safe one.
Because, yeah, it's the same difference in velocity, but you're increasing the amount of time you use to slow down. So therefore, you're decreasing the acceleration, meaning that you're making it a smoother ride, right? And sometimes you don't even have to brake because you just slow down enough and then the light changes and then you go, which is good, right? Saves your brake pads, not a bad thing, okay? So we also need to look then at the units. If you have, again, is velocity, the difference in velocity over time. The velocity is in meters per second. The time is in seconds. So our units are meters per second, which seems like a mouthful. It also can be written this way. You'll see it both ways. Primarily, though, you'll see it this way. Meters per second squared. Right? What that means is, like if you look at the gravitational pull, we said gravity has a pull of 10 meters per second squared. About a week ago we said this. That means for every second that something is falling, right? You got the pencil and it falls. For every second it falls, its speed is increasing by 10 meters per second. If it falls for 2 seconds, it's going to be 20 meters per second. 3 seconds, it'll be 30 meters per second, and so forth. That'll be the new speed. Right? So that's why when you look at roller coaster makers, they make these super tall hills, because then you're going to have a longer time to accelerate down the hill, which means you're going to have a greater speed at the bottom. Right? Gravity will be the same. So it's going to be pulling you at the same acceleration. If it's a little tiny hill, you're not going to increase that much in speed. The big hill, you'll increase a lot. Right? So Whenever you see meters per second squared, that means that that quantity is an acceleration. All right. Now, let's take a look at a problem here. I recommend with these problems, you always kind of write everything out. Okay. And when we use, by the way, when we use our friendly triangle, it'll look something like this. Sorry. Make it a little bit prettier. Okay. Well, the top will be VF minus VI, and then A and T on the bottom. Okay. So we're going to do this, and then we'll have to solve for VF minus VI. All right. So looking at this roller coaster, you have the final velocity. What's the final velocity here? Look at the problem. What speed is it when it ends up, when it's at the end of the problem? So look at the numbers that are involved. Which of those would be the final velocity? 22 meters per second. Okay. It says at the bottom of the slope, which is the end of the problem, it's 22 meters per second. Okay. And how fast was it when it started? 4 meters per second. And how long did it take it to do it? 3 seconds. Okay. And we don't know what the acceleration is. That's what we're going to find. Now, to find this top value, then we're going to do 22 per second minus 4 meters per second. Okay, and then that's going to be 18 meters per second. That's the change in the velocity. And looking at our triangle, we're going to divide 18 meters per second by the time, which is 3 seconds, to get an acceleration of 6 meters per second squared. All right.
What's number 8?
Oh, that's a question mark because that's what we don't know. All right. Okay. Is that me or is that a little bit out of focus? Go ahead and look at the lizard and see if you can do it. Yeah. Okay. Yeah. Did you get it? Are you saying you got it or? Oh, you don't have a charger? I don't. Yeah, because Emma has it. Does anybody have a charger? Okay. Yeah. Don't think I have any other ones.
I would rather deal with running 18%.
What?
Well, I'd be able to get you under the school day with 18%.
Probably. Yeah, go ahead. There you go. All right, so let's take a look at what we got here. All right, so what is our final velocity? 10 meters per second. What's our initial velocity? 2. Time is 4 seconds. All right, so then we're going to find the acceleration. You got to find the VF minus VI first. 10 meters per second. 6. So we're going to do that. I'm sorry, 2. Where did I come up 4? Then that's going to be 8. Okay. So then 8 meters per second divided by 4 seconds is 2 meters per second squared. All right. So then that's going to be the acceleration of the lizard. Any question on those problems? You got that? All right. So down here we have a couple other terms, and most of this is not going to be super applicable right now until you get into the graphing, like the instantaneous and the uniform acceleration, which you'll see more when we're graphing. What I do want to point out, though, is this positive and negative acceleration, all right? Because it is a vector quantity, meaning that it's going to have a direction to it. So when you have a positive acceleration, that means that something is speeding up, right? Whenever anything is speeding up with respect to the whoever is looking at it, then that is going to, we're going to give that a positive sign. If you're slowing down, then it's a negative, okay? So some people will still say deceleration, that's fine. What that really means is a negative acceleration. So when you hit your brake, you are negatively accelerating your car. All right. As a good example of that, let's look down here at this jumbo jet and go ahead and set up this problem. Okay, so what time is involved here? How many? Yeah, how many seconds?
5 seconds?
5 seconds, right? So this pilot stops this aircraft to turn it around in 5 seconds. All right. What's the initial velocity?
45?
45 meters per second. And then what's the final velocity?
40.
Careful. What does halt mean? 0, right? Somebody tells you to halt, they want you to stop, go to 0 velocity. So it comes to a halt, it means 0 meters per second. So to do our change in velocity, we're going to do 0 meters per second minus 45 meters per second. All right. And that looks like, that is what? What's 0 minus 45? Negative 45. Don't neglect that negative sign. It's important. All right. Then do it the same way we did last time. Velocity over time for 5 seconds. And that's going to be a negative 9 meters per second squared. Okay. Again, when you see that negative 9, that means it's slowing down. Right? But it's still going to be just as jarring to the passengers as if it was the other way. Right? So you're going to have probably lots of unhappy passengers on that plane. Because remember, we said gravity, the free fall is about 10, negative 10, and that's 9. That's going to be pretty bumpy. All right. Okay. We have one more problem to do. Now, I'll warn you ahead of time, this is a little bit more highfalutin, a little bit more sophisticated, but I'm confident you all can handle it. You've gotten the math so far, so let's keep rolling with it. We're going to set it up the same way. All right, just pretend like this doesn't exist. Or you can even, we'll even put some white out over it.
That's aggressive.
I know. There you go, see? It's all gone.
It's not.
Just ignore that for right now. We'll look at it later. Now, you have a Ferrari, we have VF, VI. Again, should just be like standard way to do things. As soon as you see these problems, just start writing that stuff down. Okay, so the acceleration is right here. All right, our time is 3 seconds. The initial velocity is 10 meters per second. And we don't know our final velocity. Uh-oh, this is a little bit different, right? Because when we do this, we're going to have to take a different approach, right? Now, here, I want you to do something. I know this will be crazy, but it'll be fine. We're going to make VF into X, just like algebra class. Okay? And put that in right here, look. X minus V sub I. All right? Actually, you know what V sub I, X minus 10 meters per second. See? Now, we know that to find acceleration, we're going to do that quantity divided by the time, which is 3 seconds, is equal to the acceleration, which is 50 meters per second squared. All right, now you know that X is going to go into the V sub F. So if it makes it easier, you can just do this. Pretend like those units aren't there. Now, if you're in algebra class, you could solve that, right?
Sadly,
Yes?
Yeah.
I'm not sensing confidence. You guys can solve this equation, right?
Hold on. It's 160 equals X.
Right. Okay. So multiply both sides by 3. So then x minus 10 is equal to 50. I'm sorry, to 150. And then x 60. And then that would be 160 meters per second. Would be the final velocity. Okay. Now, if you get all of the problems that we've done up to that point, and you're still like, with this, that's fine. We'll work on it. But make sure that you can do those other problems. That's what's really important right now. And that's what you're going to need to be able to do for your homework. All right. Now, let me show you the homework really quick, and then you can do it. You got acceleration right here. Basically, you're just doing calculations, and of course, because I love it so much, ta-da! Graphing. Woohoo!
So
I know, we love graphing, right?
No.
It's our favorite thing.
I like to connect with the dots. It's funny.
See, it's
No.
yeah, you're making pictures, right?
No, like it's satisfying to like
This is
connect the
terrible.
dots.
That's
satisfying. What is
We
it?
should
Oh,
not.
Something's wrong with
I
you.
like math.
All right. So,
Math
Maybe-
is fine. Math
so
is-
do those two, and then we'll get back together on Thursday. And that's it.
Math is graphics.
All right.
I don't understand.
Oh, we'll change that by the end of the year, Mr. Hudak.
Math is.
It's so satisfying.
They don't equal.
See, that's the problem, is you have to see how they're equal.